Namaskar everyone, self Ravi Jain works for PERMAPIPE as head of sales. I am associated with this company from last 12 years, a pioneer in factory fabricated and insulated piping. Today I will be presenting about the best practices for low temperature, high temperature thermal insulation and a new approach to mitigate corrosion under insulation. Corrosion under insulation is one of the industry sector's greatest challenge. It's a major issue that needs to be addressed from the design phase, and insulation is a part of this system challenge. So let's understand the issues surrounding corrosion under insulation. Corrosion occurs when the water or the moisture and air gets entrapped beneath the insulation, which takes a form of a localized corrosion on steel. I have broadly summarized the 7 factors that contribute corrosion. Service temperature and cyclic operation modes, duration and frequency of exposure to moisture, corrosivity of environment, type of insulation and its bonding with the substrate, conditions of protective barriers, that is anti-corrosion coating and outer cladding, climatic conditions, and site maintenance practices. Out of the above, 3 factors are related to operational piping design and other 4 factors are related to the product application. Let's understand the mechanism of corrosion. It requires the following 3 elements. One is the moisture with oxygen, the closed environment, and the initiation of corrosion reaction. The mechanism of chemical reaction is shown in this pictorial form. Iron plus oxygen plus water reacts together and forms a rust iron oxide Fe2O3. This ferrous oxide, when present with water, shall aggravate the corrosion. Mechanism of corrosion under insulation as seen in the industrial sector. A typical major refinery or a chemical plant may contain 1000 kilometers of insulated and coated pipe. Picture 1 shows the damage on the outer weathering jacket that may be due to a proper immaterial selection and poor application. Picture 2 shows the adverse climatic condition that the piping is subjected through its design life. Water ingress into the insulation system and degrades the insulation process. Picture 3 shows the water boils on the surface of the substrate and steam condenses by the time it reaches the cladding, causing aggressive corrosion both on substrate and water cladding and outer cladding. The corrosion cycle, the water gets under the jacket, most of the water cannot escape, water gets entrapped under insulation and substrate stays wet. The cycle keeps repeating, insulation becomes saturated and holds the water against the substrate. Wet insulation, regardless of what kind of dry K value you use, doesn't insulate. Wet insulation is also a primary cause of corrosion under insulation. This slide summarizes the root cause of corrosion under insulation. Corrosion is a result of water ingress into the insulated piping. Conventional outer jacket material is the weakest link in the system and are not able to sustain the operating conditions throughout its life period. Insulation material also contribute to the corrosion in following 3 ways. Providing an annular space which can collect water and other corrosive media, leaching out contaminant that accelerates the corrosion process, wicking and absorbing water and holds it against the substrate. Ultimately, failure of anti-corrosion coating and causing corrosion. Effects of corrosion under insulation. Studies have shown that about 40 to 60% of the pipe maintenance cost are caused by corrosion. Approximately 10% of the total maintenance budget is spent on repairing the damages from the corrosion. Allocated maintenance budget is rarely enough to keep up with corrosion failures. Non-destructive examinations and inspection costs are exorbitant for detecting corrosion. Insulation aging and degradation reduces the thermal efficiency of the piping system. In case corrosion under insulation is not prevented or detected in proper time, it will be a catastrophic disaster to the asset. The test standards that are available for guidance, NACE SPO 198 edition released in 2010 is one of the most widely known and respected document in this field. It offers a thorough review of corrosion mechanism, directions for protective coatings, and its limitations to certain coating technologies. However, none of the standards does not provide any guidelines on type of insulation and its application to prevent corrosion. On this platform, I request NACE committee team to incorporate the standards for thermal insulation application to collectively fight against the corrosion. A new system approach to mitigate the corrosion. Most standard NACE, ASTM and ISO, their guidelines have focused on the anti-corrosion coatings. Less research is done on the insulation material to prevent corrosion. Even less research has been done on the primary vapor barrier and its application. The least understood subject is the interface between each layers of the insulated piping system and the required properties of these interfaces to mitigate the corrosion. The current slide, the current insulated piping does not design norms is focused on below hierarchy, operational and technological constraint, installation cost analysis, application requirement. This design approach need to be reversed to mitigate the corrosion under insulation. The new system approach to mitigate corrosion under insulation, it is important to take all aspects of the insulated piping application into account, as they are all equally important to reduce the problem of corrosion under insulation. The most important aspects are the outer protective cladding, insulation, and anti-corrosion coating. In outer protective cladding, it is the first barrier of protection, selection of non-metallic jacket and its application process to form a single monolithic system. The second, insulation selection of insulation material to be focused on its thermal properties, water repellent property, and limited leaching of chloride content. Anti-corrosion coating to withstand the operating and cyclic temperature, surface roughness for bonding with insulation material, and ease of repair. This slide gives about the protective coating, the design consideration. Select the correct coating. This is the last barrier to this steel substrate. Define the temperature range, define the possible surface preparation, define the maintenance intervals and its inspection intervals, select the coating which serves the goal, weigh the coating cost up to the expected service life. The new system approach is the designers must focus on a holistic design approach to prevent the corrosion. The insulated piping is a combination of 5 layers: steel pipe, anti-corrosion coating, insulation, vapor barrier, and outer weathering jacket. Determining the application of these 5 layers and their bonding between each layer to form a bonded system. This is the need of the hour for designers to specify and to prevent the corrosion. This application design consideration, the designers must emphasize on below application and sustainability requirement while specifying the insulation material for the intended services. Thermal conductivity, this is what you pay for. Compressive strength, to have an optimum load bearing capacity. Support and pipe movement consideration, which is the weakest point in the piping. Mechanical protection, to withstand the adverse climatic condition. Fire retardancy, to serve within the battery limit area. Mitigating corrosion under insulation. Mitigating the leak spread. In case of leak, it must be confined within a single joint. Mitigating corrosion degradation by using a durable and a rugged weathering jacket. Mitigating corrosion insulation aging, preventing aging of insulation for its design service life. Product design consideration, 5 aspects of product design consideration, that is anti-corrosion coating. Second one is the insulation material. Polyurethane has a wide range of operating temperature from -196 to +149 degrees centigrade, and it is one of the best insulating material, having a low K value, better compressive strength to withstand the static and dynamic load, low water absorption, which is less than 5%, good bonding with steel substrate. When applied with spray technology, it is completely void free and prevents the path for water ingress or spread. Diffusion barrier, a 3-layer co-extruded polymer PE, aluminium PE, when corona treated, aids in preventing the thermal aging and bonding of puff with outer protective jacket. The fourth one is the primary jacket, vapor barrier to prevent the foam degradation, leak spread, and to prevent the mechanical strength during storage, handling, and operation and installation and operation. The fifth consideration is the system consideration. The insulated pipe must be designed considering the thermal expansion and contractions are negated by a bonded system and ensure the pipe support designs are optimized by providing the cradle support on the outer primary jacket. The system approach requires a testing the component and the system for its functional requirement, but the current testing standards for above ground insulated piping focus only on the components. No testing standards available to test the insulated piping system from a corrosion under insulation perspective. We can't have a system approach without a system test. The specifiers and International Standard Committee must emphasize of insulated piping system test to prevent corrosion under insulation. Understanding the layers of insulated pipes, steel pipe with anti-corrosion coating having suitable surface roughness followed by polyurethane foam insulation, spray applied which is void free and allows for visual inspection prior to application of vapor diffusion barrier and outer weathering HDP or FRP jacket to form a complete bonded system. Anti-corrosion coating. This is the last barrier to the steel surface. The designers must specify the surface profile to aid with thermal insulation bonding. Metallization, TSA or TSZ, solvent-free epoxies, DFBE, solid PU coatings are some of the good options and polyurethane is selected as an insulation material. The table provides the shear strength values with respect to the surface profile of various anti-corrosion coating. Design consideration for anti-corrosion coating. The designers have many considerations for selection of internal and external coatings for steel surfaces. There are wide range of coating selections available. Few are listed below for onshore and offshore application. Fusion bonded epoxy, external and internal, 3-layer polyethylene and polypropylene, liquid epoxies, which includes polyamide, phenolic and mastics, polyurethanes, aromatic and aliphatic, zinc-rich coatings, organic and inorganic, polysiloxanes and thermal spray aluminium and zinc spray aluminium. Zinc coating. Insulation type. The designers must focus on 3 parameters while selecting the polyurethane as an insulation material to prevent corrosion. Thermal conductivity. The K value is the most important parameter in determining the efficiency of the insulated piping system. This is what you pay for. The higher the density, the greater the thermal conductivity. The second one is the compressive strength. Compressive strength is directly proportional to the density. Compressive strength provides the loading characteristics of the foam. Select the compressive strength to eliminate the welded support, which are the weakest point for a moisture ingress. Pipe support design are optimized with pre-insulated pipe. The third factor is the closed cell content. This determines the water absorption characteristics of the polyurethane foam. Generally, it is greater than 90%. The anti-aging zero diffusion barrier. It's a 3-layer co-extruded material, PE aluminum with PE. When corona treated, having a high voltage current applied, it creates a micro profile on the PE that aids to bond with polyurethane foam on one side, and the other side it bonds with the outer jacket. The diffusion barrier has 3 main functions: preventing aging of foam, bonding of insulation to the primary jacket, and improves the long-term thermal efficiency by over 30% as compared to the conventional system. On the right hand side, you can see the graph. The green graph is the factory applied insulation and the red graph is the conventional system. The green graph remains constant throughout its design service life of 30 years, whereas in the conventional technology, the K value of the insulation material keeps on deteriorating from the day one you install the piping, and by the 30 years of design service life, you will lose the K value of up to around 40%. Why bonding is important? A bonded insulated pipe is a restrained piping system that reduces or eliminates the requirement of expansion loops and anchors. It's a kind of a virtual anchor to pipe movement. Few advantages are listed in this slide. It prevents the movement of insulation when subjected to thermal expansion and contraction, eliminates the contraction joints, prevents the gas or vapor transfer longitudinal to the pipe, facilitates even loading distribution, reduces the possibility of puncture from sharp objects, provides torsion resistance to pipe movement, improves pipe support performance, eliminate water ingress and mechanical degradation, ultimately mitigating the corrosion under insulation. Recommended quality test for bonding. As per EN 253 standard, the axial shear strength of a bonded piping requirement should be greater than 0.12 MPa. When polyurethane foam is used with spray technology, the axial shear strength achieved is 0.15 MPa. The designers must specify a bonded pre-insulated piping system meeting EN 253 standards. Pipe supports. Pre-insulated system having a good load-bearing capacity, the pipe supports can be designed to reduce welded and insulated pipe supports. Most of the supports or rest and guide shall be a cradle held from the outer weathering jacket as shown in the picture. Understanding the function of the outer weathering jacket, the picture on the left-hand side indicates this is how the insulated and jacketed pipe should always look like, but the picture on the right-hand side indicates what we see in real life. With conventional insulation system, it is expensive to build, even more expensive to run, painfully expensive to maintain. This slide shows the factory insulated piping and pipelines having non-metallic FRP and HDPE as a outer weathering jacket that can withstand the operating conditions throughout its design life without the hassle of any maintenance requirement. So a non-metallic jacket also looks pretty good when compared to a shiny metal jacket. Understanding the function of the jacket, metallic casing is the weakest link. Failure of the metallic jacket is due to the installation issues or the operating conditions leads to the water ingress into the system, especially during the shutdown periods, leading to operational problems, HSE hazards, and significant maintenance cost. The perception in the piping system cannot be sealed to prevent moisture ingress. The fact is, thousands of kilometers of moisture-proof pre-insulated piping has been installed in ground with high water tables. Today, the material science and technology allows for FRP and SDP jacket to be factory applied on straight pipes, fittings, bends, and complex spools for a piping system that can long last, avoid galvanic corrosion, and mitigate corrosion under insulation. The filament wound FRP jacket having wind down end seal, which is a bonded and a monolithic to limit the leak spread and prevent corrosion. This system can be used above ground, below ground, within the fire zone area, and outside the fire zone area. Side extruded STP jacket having wind down end seal, which is bonded and monolithic to limit the leak spread and prevent corrosion. This system can be used onshore, offshore, below ground, above ground, outside the battery limit area. The end seals are pressure tested and can take up to 11 psi water pressure, hence a watertight system. Filament wound FRP jacket is a fire retardant which is BS 476 or ASTM E84 approved for use within the battery limit area. Application and operation considerations. There are three methods of polyurethane foam process. One is the application of pre-formed sections. Second is in situ pouring of foam. And the third one is the spray foam application. The first two applications are conventional type that requires multi-layer of insulation, shiplap formation, insulation joint sealants, contraction joints, secondary vapor barrier, primary vapor barrier, pipe supports, stops with vapor stops, breathing springs. It's a multiple joint and dismounted system. Requires complex pipe support design, depends on labor skill and environmental condition. Whereas the third application method is the latest spray technology, which is completely automated and far superior to the conventional technology. Homogeneous, no joints, and it's a completely a bonded system. No contraction joints are required. Tough and durable casing, cut down the damage at site, long lasting, pipe can be supported directly on the casing, cut down on the special supports, consistently consistent quality control, and problem-free insulation system, cut down the overall system maintenance cost and maintenance-free system. Some of the slides, some of the pictures shown here reflects the manufacturing process of conventional technology and problems faced by the industry. Limitations of conventional technology that leads to disaster of the pipeline and the piping system is shown in this slide. The third process, the continuous production process technique by spray technology. Pipes are blasted to a certain profile, anti-corrosion coatings with a rough surface, and pipes are moved to the puff insulation by spray technique. Vapor diffusion barriers are applied when the foam is in the gel stage to prevent the foaming, to prevent the aging. Then the foamed pipes are side extruded with HDP or the FRP jacket for a mechanical protection. The process is completely automated with regular quality checks at each intervals. So let's see a video of this spray process, how it helps the industry to avoid corrosion or insulation.
The speed for the first inlet layer is increased relative to the second to aid in the coupling process. In the spray room, polyurethane foam is sprayed onto the application of a polyethylene bonding sheet.
This is the FRP or the GRP jacket, which is a side extruded onto the foamed pipe to form a completely bonded system.
Multiple wraps of the molten film result in a seamless polyethylene pipe along a distance of 20 to 25 feet. After the polyethylene is sufficiently cooled in the station, the unloading arms automatically transfer the finished unit to the unloading racks. The cutback portion of the insulation and jacket is removed from the end of the pipe. The end surface is cleaned up and will be coated with a moisture barrier.
This is one of the best methodology of doing the factory insulated piping, which I have shown in this slide to prevent the corrosion or insulation. This slide, I have made some comparison of conventional system versus spray technology. In conventional system, the cells are compressed. It may have voids, non-concentric. Jacket may not be bonded to the insulation. Inconsistent density, compressive strength, thermal conductivity, predetermined thickness increment, higher cost, difficult for inspection, and poor quality. All these difficulties are overcome by the latest spray technology. A system approach. To mitigate corrosion and insulation by eliminating the ingress and propagation of water within the insulated piping system by applying a more rugged, durable, and a long-lasting jacket such as HDPE or the FRP. Bonding between all layers of insulated piping system, ensuring application of void-free bonded insulation, eliminating welded supports that penetrate the jacket. To save significant cost in setup and operation by using non-insulated pipe supports, eliminating project completion delays due to on-site insulation, reducing the downtime for insulation, corrosion-related inspection and maintenance, eliminating the need of insulation replacement and repair of pipes and its replacements. A system approach needs to be designed to be a single pipe system which is bonded system having wind down end seal that prevent water ingress, rugged and durable casing and prevent insulation degradation, galvanic corrosion, and preventing the corrosion under insulation. Need of the hour is Atmanirbhar Bharat Abhiyan, an integrated service to mitigate corrosion under insulation. Most of the attempts to solve the corrosion under insulation problem is in piping system have centered on the coating applied to the substrate under the insulation. The assumption is based on many years of experience is that water will at some point of time penetrate the jacket and insulation, and therefore without a high quality coating the pipe will corrode. The problem with this approach is the water will become entrapped under the insulation and will eventually lead to corrosion due to flaws in the coating. A better approach is to pre-insulate the piping in a factory where the coating, insulation, and the jacket can be designed and fabricated to work together as a system. These systems have been used for many years in underground application where the piping is often below the water tables. The same technology can be used in above ground application. When built and installed properly, water cannot penetrate the jacket and insulation, and thus corrosion will not occur. Some of the conclusion notes to conclude: wet insulation, regardless of what kind or what original dry care value you use, doesn't insulate. Wet insulation is also a primary cause of corrosion under insulation. Standalone anti-corrosion coating to protect the asset is not an ideal solution to prevent corrosion. Factory applied spray insulation process with side extruded SDP or FRP jacket is superior to conventional technology. Aluminum diffusion barrier stops the aging process. The K factor is what you buy. The best blowing agent available is 245 Fa. Bonded system with non-metallic jacket prevents galvanic corrosion and maintenance-free system for service life. Wind down end seal are cost effective, and insurance policy to the pipeline and piping. Standards are useful as a quality assurance guidelines, but specifications should be written based on the project requirement, considering the best practices of factory insulated piping system. With this, I conclude my presentation, and if you have any questions, I will do my best to answer to the best of my knowledge.